This video is on example 11.3.2 from the textbook, which is on using eigenvectors and eigenvalues to solve initial value problems involving systems of second order differential equations. This is a system of two coupled second order equations corresponding to a pair of masses that are connected with springs. And so the setup, we have two blocks that are sliding on a frictionless interface, and to make the math easier, all the spring constants are chosen to be identical, and the masses of the two blocks are chosen to be identical. And in this case, if we write the equations of motion using Mr. Hooke and Mr. Newton, so x1 is the position of block 1, and x2 is the position of block 2 relative to their equilibrium positions. And the equations of motion then become m x1 double dot x2 double dot. That's ma, that's got to be equal to the force, and it turns out that the force can be written in matrix notation. And I'm being very careful with the minus signs here. There was a little small discrepancy in class, so I'm doing this again carefully. I have a minus out in front, then I have a positive 2k, minus k, positive 2k, and again pay attention to the minus sign sitting out in front of that matrix. And this is x1, x2. Okay, so that's just f equals ma, or actually ma equals f in matrix notation. F is going to be linear in the displacements, which is what allows us to use all these eigenvector, eigenvalue techniques. And so, again, we're going to make an ansatz. Our ansatz is that x1, x2 is going to be a perfect sinusoidal in time function. And the prefactors for the block 1 and block 2 we'll call e p1, e p2, and then the time dependence is given by sine omega p t, and then we have an arbitrary phase shift. Okay, so our goal is to compute the possible allowed values for omega p that will actually give us a solution, and then once we find the allowed values of omega p, we will go through and find what that implies about the eigenvector EP, the 1 and 2 components of that eigenvector. Okay, so we put that ansatz into this expression. We take two derivatives of this thing, and x1 double dot, x2 double dot. I take two derivatives of the sign, and out comes a minus omega squared. So that's a minus omega p squared, and then I have the same thing, ep1, ep2 times sine of omega p t plus phi p. Okay, that's mass. That's just the acceleration. So I'll just pre-multiply by mass. So this is now mass times acceleration. That's the left-hand side, and that must be equal to the right-hand side of this equation over here. So that has to be equal to the negative 2k minus k minus k 2k times the x. And remember, our ansatz for x was that it looked like this, and so here is x1 ep2, and then the time dependence sine omega p t plus phi p. Okay, and we see on both sides of this equation the signs go out, so this implies that the left-hand side and the right-hand side are equal without the signs. So this tells us that negative m omega p squared on ep1 ep2 has to be equal to negative 2k minus k minus k 2k acting on ep1 e P2, and we look at that and we have a vector times a number and a vector times a matrix on the right hand side. That is an eigenvalue problem. And so we will bring everything over onto one side, and we will say that this implies that negative 2k plus m omega p squared, that's my first entry, that matrix. Then I have a plus k, and then I have a negative 2k plus m omega p squared. So I've taken what was on the left hand side and I've added it to the right to get to this expression right here. And that's all multiplying EP1, EP2. And that's supposed to be equal to 0 because I put everything on the same side of the equation. And as we said in class, this matrix equation will only have a non-trivial solution if the determinant of the matrix in square brackets is equal to 0. So let's call that matrix M. So for a non-trivial solution, we need that M equals 0. Okay, and so we can go ahead. That's a quadratic equation. It's a very simple form, and so we can convince ourselves that m omega p squared is either equal to 3k or 1k in order for the determinant to be 0. And so we'll call the bigger one omega plus, which is going to be equal to the square root of 3k over m. And we will call the smaller one omega minus, that's square root of k over m. And then we need to go back, plug these values of omega, or rather m omega p squared, into the matrix M, and then figure out what the values of EP1 and EP2 are. Those would be the eigenvectors. So let's go back, and we'll plug in for the plus case for m omega plus squared is equal to 3k. My M matrix becomes k, 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 k. So that means that EP1, EP2, well, let me write it this way. We really need M on EP, E plus 1, E plus 2, the plus eigenvector. The 1, 2 components have to be null vectors of that matrix M. That has to be 0. And so this immediately gives us that E, the number 2 component, has to be equal to the negative of the number 1 component. And so we'll arbitrarily set the number 1 component to 1. And so the eigenvector associated with the bigger eigenvalue is going to be 1 minus 1, the antisymmetric mode. And then for m omega minus squared is equal to 1 times k, then the matrix M becomes negative k, 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 negative k, and we see immediately that now both components of the eigenvector have to be equal to each other. So E minus 1 will set arbitrarily to 1, and that tells us that E minus 2 has to be equal also to the same thing, and so our eigenvector that corresponds to the lower eigenvalue is going to be plus 1, plus 1. Okay, and so what does this mean for the solution? If we go back and look at what our ansatz looked like, it tells us that I can write the general solution to this 2-block problem as x1, x2, I'm going to have an arbitrary coefficient multiplying the plus eigenvector, and I know that the time dependence has to be sine of omega plus, but omega plus was the square root of 3k over m times t plus an arbitrary phase shift, and that has to be multiplying the antisymmetric eigenvector, and then I have another solution with a different frequency, and that other frequency is square root of k over m, not square root of 3k over m, plus phi minus, and then I have the symmetric eigenvector. Okay, so this is the most general solution to the two-block problem. So this is the most general solution to the two-block problem. Then a plus, a minus, and phi plus and phi minus must be chosen to satisfy the initial positions and velocities of the two